Hi everyone. Today we're going to have a look at proof by contradiction. So proof by contradiction is used when something would be difficult to prove algebraically that it's true. So what we do is we prove that it can't be false. So we assume that it is false, we assume the opposite, we work algebraically with that until we get to a contradiction, which shows that the assumption we began with must have been false. So let's have a look at what this looks like. We're going to prove that root 2 is irrational, meaning it can't be written as a fraction. So to begin a proof by contradiction, we assume the opposite. We assume that root 2 is rational. Now we're using this method so that the algebra works out for us. So let's write that in algebra. Root 2 is equal to p over q. It's equal to a fraction. Now, if it's rational, then p and q are integers. We also have to state that q cannot be 0, and the p and q have no common factors other than 1. So the highest common factor of p and q is 1. Okay, now we're going to work through the algebra until we hit a contradiction. So let's rearrange this a little bit and let's square both sides to get 2 equals p squared over q squared. And now I'm going to bring q squared to the other side. Whoops. There we go. So 2q squared equals p squared. And now I can look at some of the implications. So we can see that p squared is equal to 2 times something. So that means that p squared is an even number. And if p squared is an even number, that means p is an even number. So let's do a bit more algebra and let p equal to k, which is how we represent an even number. And if I introduce k, I need to say that it's an integer. Okay, so now 2q squared is equal to p squared, which is now 2k squared. So 2q squared equals 4k squared. And if I divide both sides by 2, q squared equals 2k squared. So now we can see that q squared is even because it is 2 times something. And that means q is even. And this is where we hit our contradiction. And the reason that's a contradiction is because we said above that p and q have no common factors other than 1. So that means our original assumption must have been wrong. Therefore, the square root of 2 is irrational. It cannot be written as a fraction because we end up with this contradiction of 2 even numbers. Okay, let's do the same thing for this question. So we have log base n of n plus 1 is irrational for all integers n greater than 1. So we start with the opposite assumption. So let's assume that log base n of n plus 1 is rational. And that means log base n of n plus 1 can be written as a fraction, p over q. And when we introduce p over q, they are integers. Q is the denominator, so it can't be 0. And p and q have no common factors other than 1. Okay, let's rearrange this until we've got p on one side, q on the other, and then we can have a look at the implications. So this means that n to the power of p on q is equal to n plus 1. And if I raise both sides to the power of q, I'll get n to the p equals n plus 1 to the q. Now, here we're going to look at a proof by cases. So that is proof by cases. That means I'm going to look at what happens if n is odd and if n is even. So, if n is odd, we can see that n to the power of p is odd, but n plus 1 to the power of q is even. If I look at the other case, if n is even, well, that means n to the power of p is even, but n plus 1 to the power of q is going to be odd. Now, that's our contradiction. So that means our original assumption was false. So by contradiction, log base n of n plus 1 must be irrational. So a lot of these will work out if you get, in the case of rational or irrational, p on one side, q on the other, and then often looking at cases, so if n is odd or even. Or you can challenge the original assumptions. So that is proof by contradiction, a way of showing, using algebra, not that something is true, because that's often quite difficult, especially with irrationals, but showing that it can't possibly be false because we arrive at a contradiction.